So it's a pleasure to have today's speaker, Professor Gary Fetter from Carnegie Mellon University. Gary got his bachelor's and master's degree in electrical engineering and computer science from MIT, and then did his PhD in the same subject at UC Berkeley. He got to Carnegie Mellon in 1994, and he is now the Howard M. Wilkoff Professor of Electrical and Computer Engineering, with also appointments in mechanical engineering, biomedical engineering, and the Robotics Institute. He's also the director of the Manufacturing the Futures initiative at Carnegie Mellon, and has had a number of past administrative roles at the university, including vice provost for research, among others. Gary's been heavily involved in the U.S. Advanced Manufacturing Partnership, which led to the National Network for Manufacturing Innovation, and actually led the Advanced Robotics for Manufacturing initiative until last year. He won an NSF Career Award in 1996 and was appointed a fellow of IEEE in 2007. And I'm going to turn it over to you, Gary, and I'm eager to hear what you have to say.
All right, thank you very much. Thanks for the kind introduction, and I'm really pleased to be able to give this talk today. I thank Oliver Brand for reaching out. I was pointing out to him right before this talk that I've been working on this area of soft interconnect for about a decade. I got started right around 2010, actually, with neural probes, and I haven't really pulled everything together in a overview talk, and this is my first shot at it, and it won't be comprehensive, but in terms of everything that I've been doing, but focused on some of the more recent areas. So let's dive in. I did feel the need to just spend a segment, given the time we have, to talk about some kind of culmination of work I've been doing on neural electrodes and some of the recent work on neural cuff. So I'll touch on that briefly, and then most of the talk is going to be about electronic skin technology and what we're doing in aerosol jetting in that area. So we started a few years ago working with a team from the University of Pittsburgh at the Hillman Cancer Center, led by Charles Horn, who works on this area of on cancer issues, and mainly issues about nausea in the gut and that sort of thing. And we were hypothesizing that we could use parallene probes that we've been making for quite a while for brain probes and use these as cuff electrodes on the vagus nerve to do some electropharmacology, if you will, and perhaps even be able to kind of study some of the therapy for cancer, for immunity to anti-tumors or to tumor growth and that sort of thing. So our technology has been using a parallene platinum electrode with a hydrogel adhesion so that we can make multi-electrodes around the vagus nerve. Chris Bettinger at CMU, the colleague that has worked on the hydrogel, and the other folks at University of Pittsburgh focused on the surgery for that. And so this is kind of a culmination of work we've been doing over the years in making multi-layer conductors in parallene. This is all thin film processing, stacking the parallene and then platinum and so on. And this is a fairly generic process here, unlike some of our other peripheral nervous probes. But the design is actually what's interesting. We have a long cable that goes to the working region at the bottom of this screen here, where we've got some flaps sticking off of the cable, and these go to individual electrodes. And since these are gonna wrap around the vagus nerve, we wanted to make the electrodes long enough to increase the amount of amount of area we're going to be able to stimulate per fiber, but localize where those electrodes are around the circumference of the vagus nerve. So in terms of the technology, which is really kind of the theme of this entire talk is technology, is we had to size this for the mouse vagus nerve. It's around on the order of, I believe, 300 micron diameter was what we were shooting for this particular design. And what we found is we needed this very thin parylene, meaning on the order of 4 microns thick, to wrap around the vagus, but we needed a much more robust cabling system. So we had made the cable out of the parylene when we first started working with the surgeon on this. They're breaking them all the time. So we ended up casting PDMS on top of the cable, but not on top of the working region at the bottom. And so you see the cable here, it's actually a piece of PDMS with this parylene embedded in, and then we've got a zero insertion force connection that we made by putting the polyimide stiffener and then a breakout board. The other interesting thing was we spent quite a while. We had to figure out how to get this to work where the surgeon, in this case Charles, was going to not break these before he puts them in. And so we found that by putting these in straws, it would be helpful, but the plastic straws ended up charging and having the probes would stick and then they would break inside the straw. So very simple solution there was by lining it with paper, it solved the problem, but created a very nice delivery mechanism for the surgeon. So yeah, this is the working task was, this is in a mouse. You can see a millimeter is on this ruler here, but the hydrogel, what we do is the hydrogel here in the schematic is in green, and we lay the probe down on top of the hydrogel. It's on top of a piece of parafilm so that can be peeled off by the surgeon easily. And then that whole parafilm setup gets registered under the vagus nerve, and then they wrapped it around to intimately connect the electrode onto the vagus nerve with this. So in a way, think of it as a hydrogel suture without having to. So it just glues together, almost like a taco shell. And so that worked, and we were able to get selective stimulation out of that, not in every mouse in every channel, but giving you here's some examples of the compound action potential, blood pressure, heartbeat coming out of a typical animal. If you look at the channels, we had 4 electrodes, so the 4 channels, 2 of the channels were highly selective, channel 1 and channel 4, where we're trying to stimulate the compound action but not affect heart rate and blood pressure. You can imagine that that type of thing would have practical consequences in for example, human stimulation, where you'd want to stimulate the vagus nerve going down to the rest of the peripherals, but not to maybe, for example, the heart would be not where we'd want to go with that. And so looking at the aggregate of these experiments they did, there was many channels that had very good ratio of good compound action potential and no blood pressure stimulus, although we did have cases where we were stimulating everything. So here's a case where having a multiple set of electrodes around the vagus is useful, and then using learning techniques, for example, to identify which of these you'd want to stimulate. So I just wanted to touch on that to give you an idea of what we've been doing on the neural probes. And this is one of the reasons I did this historically. This is what kind of got me into looking at soft technologies. I mean, for the first 30 years of my career, I've been focused on physical microelectromechanical systems and looking at silicon and silicon dioxide and so on. I didn't really think about polymers too much, but this experience kind of launched me into thinking, well, what else can I do? And I got interested in this electronic skin area, very busy area, but I linked up with a faculty member here at Carnegie Mellon, Rahul Panad, in our mechanical engineering department that specializes in aerosol jetting, and we've been making some inroads in this that I think are kind of interesting and hopefully helpful to help push the field forward on the technology end. So let me launch into that for the rest of the talk. Just start with level setting about electronic skin. This is, as I said, a very busy area, both in academia and also starting to be commercialized, about being able to, imbue perception, control, sensing, actuation, basically all electronic sensing capabilities into a stretchable, conformal, and really biocompatible substrate. Because when we say skin, generally we're thinking this is going on human skin. It doesn't have to. It can go. In fact, we're looking at how do we apply these things to robots and other types of objects, not just humans. But the human application really drives a lot of the motivation for this in health and wellness monitoring, displays, haptics displays, ultrasonic imaging, prosthetics, even cosmetic applications. There's going to be as these technologies mature, there's going to be folks that will just really want to wear these because they're going to be cool. But a big part of this is there's a lot of work out there in making wearables. The intent that I'm kind of looking at is this niche area of making them non-invasive and for chronic use. So really having them stick to the skin and then you can just forget about them. And so busy area, we could spend an hour or more simply reviewing this area of all the work that's been done. There's been many wonderful reviews about electronic skin and research. This is just a handful of those areas, but I picked a few I thought were interesting. Epidural Electronics, this is a kind of a landmark paper by John Rogers' group in 2011 in Science that kind of, it sort of introduced the subject to a lot of folks. They spun off a company called MC10 to commercialize some of these technologies, which have resulted in more like soft patches at this point. So one of the things I underscore about that technology is, which is very relatable to what I'm working on, is this idea of embedding physical wiring inside of PDMS or other elastomeric compounds. And if you make them thin enough, you can get them to move with the skin and wrinkle, like you see in this lower right left picture. The second kind of idea is liquid metal electronics. The reason liquid metals are interesting is because they're flexible and they're not going to crack and break. There's a lot of challenges in that. I picked out, there's another very busy area. Oliver Brand at Georgia Tech is working in this area. I picked one of his papers to highlight here. A couple of my students from former students who are now at the Army Research Lab, Sarah Bader, Nathan Lazarus, and their team are working on liquid metal for, in the center picture, for power transfer, inductors, capacitors, that sort of thing. Carmel Majidi is pretty well known in the area for working on these stretchable electronics, and he has a spin-off company as well for this. And then there's international folks. This is a group from Korea that's been working on liquid metal electronics. And last, again, very busy area, but there's quite a bit of work, obviously, on organic electronics. I picked this from Japan. I thought it was a compelling picture showing kind of the vision, the concept of having, in this case, organic LEDs that can be placed inside of PDMS and stuck on. So there's no lack of motivation, ideas on design, putting these together. So why am I working on this? I'm interested in making this technology be more robust and more manufacturable. I think there's a long haul in this. It's not going to happen overnight, but the attributes that I see that really would make this be a highly interesting, commercially, is if obviously we want to make this elastomeric conformal to the skin, and that unless you're doing it over a joint, that means you strain of at least 40%, so you can do wrinkling, the kind of things you see in the picture on the wrist and so on. It's got to be skin safe, so I've been steering away from liquid metal, even though it's okay. Usually the liquid metals, they'll absorb into the skin. They're non-toxic, if you will, but I think for most applications, folks are going to want to wear things where they're not worried about that aspect. The thicknesses have to be sub-millimeter, and typically you want these to be less than a tenth of a millimeter so that they conform to the skin well. An important area is the wiring conductivity to be low, and we're trying to look at how do we make this close to bulk metal so that we can just simply wire circuits up. There's a lot of work on other types of stretchable conductive interconnect that isn't close to bulk metal, and that's interesting for things like sensors and certain applications. But if you're working in power or just regular circuits, having low conducted interconnects important, or high conductance interconnect is important. And we want to make it multi-level so that we can interconnect various chips. And then last, we've been focused on doing this in 3D printed technology for on-demand manufacturing. And that 3D printing that we're looking at is aerosol-jet. This is, for those of you that aren't familiar with aerosol-jet, it's an additive manufacturing technology, a 3D printing technology that uses either pneumatic energy or ultrasonic energy in order to create an aerosol out of an ink. That ink can have nanoparticles in it. It can simply be polymers dissolved in a solvent. These droplets, micron scale droplets in an aerosol, then get blown through a tube and through a nozzle. And the key is that there's a sheath gas on the nozzle that focuses then this into a stream that you can then get direct write. The nice thing about this that's better than inkjet technology is that this is not drop on demand. This is a constant stream, but you can get substantial amount of material out in a short amount of time, whereas inkjet, there's a time issue of getting the enough droplets out to create appropriate structures and so on. So this is thought to be a reasonably manufacturable type of process, and in fact, Optimec is one of the companies that kind of specializes in this area. You see Professor Panat here with his mask on, opening the machine we have at CMU. The aerosol system is over on the left, and you can see something on the platen that they're printing. I think this is probably printing on polyimide right now under the jet. If you look at the jet, you could typical nozzle sizes are anywhere from 300 microns down to 100 micron, and it shoots this aerosol in this case, the smallest beam size would be on the order of 10 micron. I got a short video, if I can work, that just shows the in this case, aerosol-jet printing of a inductor. This could make you a little car sick if you're prone to that. And then do overpasses on that in order to get thicker and thicker structures. So that's kind of the principle behind it. And Rahul, in his group, he's worked on a lot of different types of structures. Aside from the sensors you see on the left, temperature sensors, moisture sensors, this is combining various materials together and obviously design concepts. On the right, it's quite exciting that he's perfected how to use this technology to make 3D microstructures where the aerosol jet is focused in a region and can build up to make complex structures like the potential antenna structure on the bottom, these kind of wiring, in this case just for demo, showing it connected to an LED and it actually works. And he's got an NIH project with Eric Guitry, a professor in biology at CMU, to work on neural probes as well. And so you see some of the amazing 3D structures he's making. And this is all done with that aerosol jet printer, and it's done in such a way it's on a heated substrate. So as the jet is impinging, it solidifies immediately, and one can create these 3D structures. One can do this with polymer too, both with heat, but there's also a point UV polymerization system, so you can have the UV light turn on as this thing is jetting and just freeze the polymers. I'd be remiss if I didn't point out Rahul Panat's recent work on this with pillars. He's created a COVID-19 detection system, which he teamed up with researchers, in this case, a Dr. Gao at the Hillman Cancer Center at the University of Pittsburgh, and his postdoc, Dr. Ali, who's in the upper right, to create pillars that have a large surface area, and that helps to put on this reduced graphene oxide, or RGO, which then acts as a binder to the SARS antigen. And in fact, they tried 2 different antigens for 2 different COVID-19 antibodies, and found, as you see in the lower right here, with electrochemical impedance spectroscopy, where they sweep frequency in the between a working electrode and a reference electrode on their electrochemical miniature microfluidic setup, they're able to identify within 11 seconds that there's a SARS-CoV antibody present. And so that we think is obviously pretty exciting, but also what's also interesting about this is this system can get regenerated within on the order of a minute flush of the system with formic acid to clean off, and then clean off the antibody, and then it's ready for reuse. So they're looking at how to take the next. So that's kind of an introduction to aerosol jet, and then so what are we doing? We got a couple of grad students, Rahul's student Jacob Brenneman, my student Daria Tansel, have been teaming to do polyimide silver interconnect on PDMS. You can see kind of the setup here in the upper left with a polyimide that's dissolved in NMP using the pneumatic atomizer. These are for those of you that are interested, these are the settings. And then using a silver ink from Clariant that is commercially available and diluted with DI water in the ultrasonic atomizer. So this 3D printing is done serially, layer by layer, to build up these structures. And the process looks as seen here on the left. Right now, we're just doing a single layer process. As you'll see, plenty of challenges. We're very pleased that we've worked through them, but still a lot to learn. What we found is we're getting on the order of 2 micron per pass on whether it be silver. This is 1 pass of silver with a narrow nozzle, and then we're using a wider nozzle because we want to coat with the polyimide and also on the bottom. These are just overlaid traces of test structures. So you see the basically linear relationship of passing the 1 layer of polyimide, 2 layers of polyimide, 3 passes of polyimide. And you can see the waviness, and that's because of the passes and choice of overlap as the jet is flowing across. The jet's probably covering on the order of 30 microns per pass. So one has to go raster scan that to get enough width. And then, of course, the picture at the top, you're seeing the silver, and then the top polyimide just got started where you see the dotted line. So, we got to walk before we run. So we got started thinking, hey, we're going to make an EKG patch. It's the simplest possible thing. What could go wrong? And so that's what we got started with the vision that we're going to make a very thin PDMS patch, put these wiring in, and have some electrodes sticking out. We got this idea of electrodes from, again, we have the pillar technology that Rahul has, so why not exploit that pillar technology and have these things stick out so that we can interconnect with the world or with chips or whatever. In this case, it's the intent was with the body. And Jacob Brenneman, who jetted this, liked the idea of having these kind of cylindrical structures as opposed to solid, primarily because it takes less time to jet. But there may be some advantage forward. So now I'm going to dive into, well, what we said, what could go wrong? A lot can go wrong. And so let me start that saga and show you where we've been. The first thing that can go wrong is the PDMS will not work. And so what we found early on was, of course, PDMS, especially the Silgard 184 that we were using, isn't meant for high temperature. The vendor wants this, recommends this gets cured anywhere 60 degrees, 100 degrees centigrade on that order. So we're trying to cure this at 200 degrees C, 350. Why? Because we want to sinter the silver that we were jetting, and also cure the polyimide. Well, when you cure the PDMS in air, it decomposes and it cracks, fractures. It looks like broken glass on the wafer. However, we did find early on that by putting PDMS in a vacuum or in an inert environment like low vac 1 torr nitrogen, we don't get the cracking. And in fact, it also releases from PAA. We use polyacrylic acid for a release layer. It's actually a very nice release layer for this because it's pretty robust to all the thin film processing we need to do on top, and it releases just in salt water. So quite nice. So then, but we embarked on, okay, well, we could anneal this in high temperature. What happens to the material properties at high temperature? And we looked in the literature and really couldn't find anything definitive about that, except for people to say don't do it. So we embarked on this. We spin cast a bunch of wafers with various types of PDMS, and then used a so-called curio cutter. This is a commercial machine. Cut out, in this case, we cut out dog bone shapes that ASME type of tensile structures. and put these in an Instron machine and pulled, as you can see on the right, to get load extension curves, or so-called stress strain curves. In this case, this is what's shown as a typical Silgard 184/20:1 that's just cured at 100 degrees C. So this is kind of a baseline for 20:1 PDMS and what happens. So you can see that it's hyperelastic if you get to extensions that go above 40 millimeters. I think it was a 10 millimeter extension. So I'm actually not sure exactly what that strain is, but it's you can see here that we're going, in this case, we're going 3 times the length. So I think what we're seeing is on the order of 300%. Well, here it is on the top, I'm sorry. So yeah, 300% type of strain to failure. But we're seeing the nonlinearity kind of kicking it at 150%. So if you look at high temperature, what we find is that we tried to do these cures at 1 torr in vacuum at 100 degrees C, 200 degrees C, 300 degrees C, and just no extra cure in vacuum. Okay, so all these samples that we did, A, B, C, and D, and E, were all cured in air at 100 degrees C, and then we added extra curing to the C, D, and E samples. We also did a 10:1 PDMS, again, just as a baseline to see, because 10:1 is what the vendor, that's all they supply in their data sheets. They use it 10:1. So as you might imagine, you do in the orange B case, 20:1 PDMS, we get a lower Young's modulus. What's interesting is that the cure in vacuum at 100 degrees C, 200 degrees C, 300 degrees C doesn't really affect the Young's modulus significantly. In fact, the Young's modulus goes up a little bit, but then it starts going down. And we think that has to do with decomposition of the material, not really the, obviously there's no oxygen, so we're not affecting the bonds with oxygen, but probably effectively burning some of the material to make it a little weaker. What's interesting is the strain to failure, that we were able to get reasonable strain to failure. Even at 300 C, the strain to failure was on the order of 100%. However, ultimately, I'll just cut to the chase. I think we're settling on this 200 degrees C curing, and that's because we think we can. We're going to get reasonable silver sintering. So we have to balance our PDMS and our silver sintering appropriately. I'm going to have to speed up, I think, because I realize it's 9:40. So we did modeling on this. We used what's called the Ogden Model for this. I'm not going to go through this math, but just wanted to emphasize that modeling is important. And in fact, in this case, the model works incredibly well at fitting, and it is just an engineering fit to it, but it's helpful to have this. This is helpful. The finite element analysis matches this as well. And then we found, when we're doing these Instron tests, we had to figure out how to do the sample prep. So we created rigs to be able to handle these things, which are, if you think about it, they're sub-millimeter. It's like handling cellophane, and there's a danger of them sticking together. So we did some preliminary stretching experiments with this polyimide wiring, and with different, and this has been done in John Rogers' group and other groups. There's a lot of groups that work on these computers, and we simply wanted to have our own baseline information on this, and finding that here we have this PDMS with this meander wiring of polyimide and silver, and in fact, we're able to get stretch. You can see here that we get failure at an extension of around 7 millimeters. And again, I don't have the strain on here, but basically that's that's going to be 3x extension. Notice the jagged nature of the load versus extension, and that's actually a micro failures that happen where the polyimide wiring is actually delaminating from the PDMS in specific locations along the meander, and that starts happening at about a millimeter extension, and then it just keeps popping, if you will, like a zipper up. But it's amazing how strong the polyimide is. It's also interesting to note that throughout this whole, until the failure, the resistance stayed at a low level. And if we, looked back at this, we'd see that the resistance here as I go through this. There we go. So you can see the resistance, and I'm going to stop it. So the resistance here is on the order of tens of ohms. So it is, I think, under 100 ohms. So we're very happy with this. Before release, it's like 100 ohms, and then there's only 120 ohms, going through this process. So that was problem number one, was the PDMS. The second problem we encountered was really interesting, is this issue of delamination of the polyimide. So we'd made these meander patterns. Here you see a meander patterns of interconnect where you see delamination clearly in certain regions and not others. And what's happening is we're getting delamination in regions where we have 50 micron wide lines at the ends, and where we have the thinner 30 micron wide lines, we don't see the delamination. And this delamination is happening at the very end of our process, where we do these 300C PDMS cure, and then the polyimide cure, and then the silver center, and then we put the aerosol-jet, the polyimide on the top, and do a cure. And it's during that cure that we're seeing this delamination. What's going on there? So it's clearly dependent on the silver width. Okay. It's also dependent on the polyimide thickness. We found that when we would aerosol jet single layers of polyimide, we got beautiful wiring. This in SEM, and here this is a triple layer of polyimide, so it's on the order of 6 microns thick, and we're seeing the clear delamination, and it's delamination of the polyimide to polyimide. It's not peeling from the PDMS. The polyimide, the bottom polyimide, is staying on the PDMS. It's literally peeling apart the first and second layer. So what the world is going on? We did some modeling on this, and what we found was, of course, polyimide absorbs water, well known, a lot of water sitting in it. And at high temperatures, our hypothesis was the water is getting into the void where the silver nanoparticles are, and it's vaporizing and creating a vapor pressure, and that is creating the energy for cracking this. It turns out that's exactly what's going on. It isn't kind of thermal expansion driven. This is driven from the vapor pressure, and we literally are seeing pressure build up in this cavity, and eventually it creates a crack propagation, and that's what's creating this issue. And so if Jacob Brenneman was the lead on this. He created an analytic model of this with energy release rate, which is the rate of change of strain energy in the system as a function of the crack area. And a lot of times we think of energy release rate per unit length in this case because we've got a line, so it's a derivative of with respect to the crack length, which in our case is 2 times A. And what we found is with this model that we plotting crack length versus energy release rate in both of these two plots. And the one on the left has a fixed top polyimide thickness. So we're varying the bottom polyimide to 4 6 micron. And notice as the bottom polyimide thickness gets thicker, the energy release rate goes up. And that's a bad thing, because when you get above a certain limit, in this case showing this dotted line, we have the problem of delamination. So bottom thickness matters a lot. What else is interesting about this is, there's these two regions that you see here distinctly in the model. One is at small crack length where there isn't much volume, but there's an ample amount of liquid that the water gets into that volume, and it saturates and creates a pressure, a saturation, and so you get the pressure from the vapor saturation, and that's not dependent at all on the bottom layer thickness, because there's plenty of water. But then we hit what's called the so-called vapor starvation region, where the crack becomes so large enough. Now you have a large enough void. There isn't as much vapor to feed that volume, and then we get into what's called the vapor starvation region, and all of a sudden the energy release rate kind of plateaus and starts to go down. The other thing about the vapor starvation region as it goes down is that as the crack length gets larger and larger, that energy release rate is not dependent on the top thickness. It's only dependent on the bottom thickness, as you can see in the right plot. And so this gives us a lot of good insight into what's going on. And so you can see this is where the crack propagation is, and we can predict then where are we going to delaminate. I don't have time to walk through all this, but you can plot. What we did is plot 3D plots of the energy release rate versus the top and the bottom polyimide thickness for various crack widths, and a crack width in our case is how wide are we making the trace? Are we making the trace 60 microns wide, 80 microns wide, or whatever? And what we find is that as we make the trace wider, it changes the delamination region, which is, for the case of the 60 micron trace, we're going to delaminate, according to the model, in this purple region where we have a large bottom polyimide and actually a modest top polyimide. But then if we make that wider, what we find is that the delamination region widens out to this whole right side, and now we still want to get no delamination. We need we basically want a small polyimide thickness on the bottom and on the top. But you can see it's kind of complex. You get different design choices for this. So we solved that problem. So we understand what's going on. Oh, I should mention the other big thing is that's kind of obvious after doing all that is, well, one of the main things to do is before you're going up to 300 degrees C, dry out the PI, dry out the polyimide. So having this drying step is critical. This just simply underscores that fact. So we made pillars. You can see here we talked about the pillars already, and so the third problem we had was cracking. And for the cracking, the issue has to do with like fast evaporation. I'll get to that in a second. But you can see when we were making these devices and we were putting them in vacuum, we were getting these small cracks, but very distinct cracks around the pillars. And we also, early in our studies, we noticed we were getting cracks in wires and other features that we were aerosol jetting, and didn't really understand exactly how to avoid that. But then in other cases, here in samples 1 and 2 at the top, it's hard to see, but there are no cracks in these. But those are done at atmospheric pressure, and then we were fiddling with the ramp rate and so on. and you can see, getting much better conductivity as well in the silver by heating it at atmospheric pressure. So what's going on there? A couple things. One is that when we're curing in a vacuum environment, we were getting rapid solvent evaporation. In the literature, here's one example. It's clear that the tensile stress in the film is going to be directly related to the evaporation rate of the liquid. So evaporating slowly is important, and this is where the drying comes in. So having the drying step instead of putting this at a high temperature furnace and vacuum immediately is a critical thing. And then the second thing we noticed was this issue about the conductivity of the silver, and that if we were trying to do this in a vacuum environment that doesn't have oxygen, we were getting poor sintering and wondering what's going on there. And remember, we need to put the samples in a vacuum nitrogen environment because of the PDMS, so we don't really have a choice there. So the issue there is that for the sintering step, it's important to remove all the surfactant, or as much as possible, from the nanoparticles in order to get proper sintering. And oxygen plays a key role in effectively burning off that surfactant or evaporating, getting rid of the surfactant at those temperatures. And so we kind of had a conundrum there of what to do. And so we tried a bunch of profiles. And bottom line is, and this with using 4-point resistance test structures to look at the conductivity, what we found was on the red we're getting cracks, right? So that's bad. Even in some cases we were able to do the test structures and see what the conductivity of the wiring was. But, the cracks is a no-go, and that was happening. Because we were either not how do I say this? We were either not in air or not doing the drying step. Okay, so the first one was no drying step. We had drying steps for all the other ones. So it's important to do the drying step in air, and that's so we get the low, we get the good, high conductivity of the silver, but we also get no cracks, because in the we're able to do the drying first, then we can go into this inert environment. And what we found is we can lower down to the 200-degree temperature and get reasonable conductivity and do a trade-off. While we could go at 300, we found that the 200 we're going to get better PDMS behavior. So this is our recipe now, and so we have a certain profile going through this of, again, a drying step at 150 C and then going up to 200 in the vacuum. So limiting the air exposure at to 150 for the PDMS is critical. Oh, and then you get some nice pictures. You can see the sintering of this. Here's an example pillar where we're getting, if you look carefully here, there's a certain amount of porosity to this, but it's fairly well sintered, and we're getting good results. And we're able to really, this is a recent example of a released device. So let's see. I've got I'm going to skip over some of this, but this is my last segment of the last thing. Remember when we were doing the pull test, we were having the PDMS, the polyimide pop off the PDMS and create these kind of sawtooth waveform in the stress strain curve on the tensile test machine. And so this is actually earlier work I did with a student, Nazar Nassarafar, along with Professor Phil Leduc in mechanical engineering at CMU, where we were studying, well, can we use curing agent in PDMS and actually kind of localize the stiffness of the PDMS, and how much of a difference would that make on delamination? At the time, we weren't thinking of it for the polyimide delamination, but that's equally important here. It's delamination of chips that are embedded in. So we started with making discs of 5:1 PDMS and embedding them in 20:1 PDMS and looking at okay, if we stretch these and have as a parameter how big the disk is around that, what happens? And we do find that if we can make that Young's modulus difference large enough, and we can make a large enough disk, we can get a lower energy release rate for a given, in this case, 5% applied strain, but it would just go up linearly with that here. We'd be shifting the curve up and down. And so it's important to have a certain amount of a larger Young's modulus, as intuitively obvious, I guess, around a rigid chip for this to work. And in fact, doing these validation experiments, pulling on chips with 20-to-1 PDMS, indeed, even at 30% strain, we were getting a delamination. And of course, if these were wired, the wires would just break. However, putting the 5-to-1 PDMS around the 21 PDMS, even up to 100% strain, we didn't get breakage. What was interesting is we started getting delamination at the 5-to-1 PDMS, 21 PDMS boundary, not at the chip boundary. So all of the interfaces are important. Then we did another study where we took that a step further and said, well, can we drop cast, and what's the effect of drop casting PDMS as opposed to just creating solid chunks and embedding them inside? And so we did hybrid, where we had solid chunks at 5-to-1 PDMS, and then that was what we did previously, and that's a control. And then we drop cast 5-to-1 PDMS in addition to kind of make a diffusion region around that. And then just tried 5-to-1 PDMS drop cast without any solid chunk in the middle and see how does that protect the chip. And when we did those kind of pull tests, we found that this is some work on contour mapping with carbon black, if you will, on top. You can see the center is having the disk, the 5-to-1 disk and the drop cast, and you can see a nice smooth transition of strain. And indeed, it's that sample you get the best highest failure strain percentage. In this case, around 135% before we started to see delamination anywhere in the system. So then we tried inkjet printing. Again, in the interest of time, I think I'll skip over this, but we did try inkjet printing at the time on this to distribute the curing agent, and did some tensile tests and showed that indeed we're able to localize the strain. The student graduated before he was putting actually chips in this and trying our prior thing, but I think that would be the next step. But we kind of now are thinking we're moving to the aerosol-jet, and we have tried aerosol-jet and curing agent that works. We've also tried, we made just for fun some freeform structures with this, where you jet the curing agent directly into the base PDMS. So and then you're just curing the parts that have the curing agent and can make freeform structures. This isn't nearly as fine grained as you get in a PDMS 3D printer, but we also haven't fine tuned it. So I think there could be more to go. So let me conclude. A lot of technology here. Where we're heading with this, and what I'm excited about, is making a batch flow of with this 3D printing technology, and this is all the different steps. But basically, do multi-layered systems where we're using these pillars to do vias in between the layers in the interconnect, and also the pillars to get out to system, and also those pillars to interconnect with chips and then embed them. So we think we've got a good start now, because the interconnect is working and not cracking and low conductivity. So in the next year or so, I think you will see us getting to this point. So just to conclude, this has been a technology talk. I just my emphasis here is a very busy area, this soft electronics, but there's so much opportunity in the area of soft interconnect and the technologies, because there's so much to do to make this robust. And obviously the motivation is there to do it. There's plenty of creative, exciting applications that people have already shown, but they haven't been realized as products yet. So in conclusion, or I want to just end with the acknowledgments of the students' work that I showed today, the faculty collaborators, and see the funding down there. Thank you for your time, and I appreciate the opportunity.
Great. Thanks very much, Professor Fetter. We really appreciate you spending the time with us. I think we probably have time for maybe one or two questions. If you want to enter it into the Q&A box, you can do that. I do see one question so far from James Yu. Do you have to cure or sinter the silver ink in the polyimide silver interconnect?
Yes. Well, because let me stop sharing. I think I can see you guys. Yeah, I think it's important to be able to cure the silver inside the polyimide. In fact, because that's the whole idea, right? You're doing the interconnect where the polyimide is encasing the silver to structurally protect it because the polyimide is a tough material, and so it's going to help protect mechanically the silver, but also electrically to insulate it. Right? Actually, what's kind of important on the curing is that, and this is true in almost all processing, right? That you need to cure your prior steps. Always have at least the same temperature as your steps following. So whatever, when we're curing at let's say 200 degrees centigrade maximum on the silver, it means that we really want to make sure, even at the front end of the process, that the PDMS and the polyimide are cured at that point. Now at the very end, once you're done with the curing of the silver, one could lower the temperature. For example, our last layer of PDMS, we wouldn't cure it at 200 C because it would be advantageous to be able to cure it at 100 C, so we get a little more elasticity of that top layer.
And Oliver, did you want to ask your question?
Yeah. Hey, Gary, my question was about the 3D printing, basically with the aerosol-jet printer, the structures that you showed at the very beginning from your colleague.
Yeah. Right.
What are the minimum dimensions that he can print in that 3D method
in the 3D approach? I think so when he's doing the needles, the tips, he's getting down to on the order of 10 micron, to the critical dimension of the aerosol jet, down to 10 microns. I think obviously just structurally one would want the base to be more rigid, so like on his needles they kind of taper up. On the COVID detection structures, they were at 75 micron diameter, but I know they can go, again, I think you can get down to around the 10 micron level, but maybe I think getting pillars exactly at 10 micron would be a challenge, I think. So probably I would be more confident with something like 25 micron.
Okay, thank you.
Yeah.
Great. I think in the interest of time, we will call it a day today. Thank you again for your excellent presentation. And to everybody who's still on, we'll see you next on April 26th for the next nanotech seminar. Have a good day, everybody.